Okay, so we've introduced a very important rule at the end of the last video for the power rule. Right, the power rule, very important. We've looked at basically three differentiation rules so far: the constant rule, the rule for the natural exponential function, and the power rule. Now I want to extend the rule so that we'll be able to find the derivative of any polynomial very quickly. In order to do that, we're going to need the following three, I guess technically, linearity rules. So if f and g are both differentiable functions, what's it mean to be differentiable? It means the derivative exists, remember. They're both differentiable functions, and c is any constant, any real number. Then the functions f plus g, f minus g, and c times f are all differentiable functions. And the derivative of the sum of two functions is equal to the sum of their derivatives. So if I'm finding the derivative of sum, I just take the derivative of each individual function and add them. The derivative of the difference of two functions is the difference of the derivatives, and the derivative of a constant multiple of a function is just the constant times the derivative. You can pull that constant outside, if you will, the differentiation process. Okay, so I'm going to prove this one here. The others can be proved very similarly. And to do this, I'm going to let p of x equal the function f of x plus g of x, so that I'm finding p prime of x. By the limit definitions, the limit is h goes to 0, p of x plus h minus p of x all over h. All right, that's the limit definition for the function p. So what is this now? This is the limit as h goes to 0. P of x plus h would be f of x plus h plus g of x plus h. And so that's the first one, minus p of x, which is f of x plus g of x. Now be careful here, I put this in brackets because it's real important that we distribute that negative sign over. And so when I do that, what do I get here? Minus g of x. Okay, so far so good. Again, if I plug in h equals 0, it's indeterminate. But I'm going to break this up a little bit first of all to see if you'll see where I'm going here. I want to sort of regroup these terms when I'm adding these things. Say I'm subtracting here, but I can think of this as plus a negative f of x plus a negative g of x. I can rearrange, right? Adding is commutative and associative, so I'm going to bring this plus a negative f of x or minus f of x here, plus g of x plus h minus g of x. I want to regroup that way up top. So I haven't changed anything. I've regrouped the order that I was combining things up there, but it's still the same. All right? I can do that with addition. But now here's what I'm going to do. I'm going to split up this into the sum of two fractions. And I think you'll know why after we've done this. Can I do that? Can I just go to here? Yeah, think about this. If I was adding these two fractions, what do we need? A common denominator. Do we have a common denominator? Yeah, it's h. So I can simply add this numerator to this numerator and get this, right? So these are the same thing. But now I have the limit of a sum of two functions. Well, we know the limit of a sum of two functions is the sum rather of the limits by the basic limit laws. So it would be the limit of this one plus the limit of this one. And this is really where the linearity laws for derivatives come into play, because the limits have these same linearity laws. So what is this? What is the limit as h goes to 0 of f of x plus h minus f of x over h? Well, this is indeed the definition of f prime of x. How do I know that f prime of x even exists, though? Well, because we were told what? That the function f and g, what? They're both what? Differentiable. So because they're differentiable, I know f prime exists. That limit always exists. That's the definition of f prime. This is the definition of what? G prime. And so we get exactly what we said we were going to get. The derivative of the functions f of x plus g of x, the derivative of the sum of the functions, is equal to the sum of their derivatives. And that's the proof. So these linearity rules open up a bunch, right? We can do sums, differences, and constant multiples and find the corresponding derivative. So let me show you now how we can differentiate a polynomial function. Okay? And I'm going to do it really in all of its glory here. So, what is the derivative p prime of x? If p of x is this polynomial function. Okay. Well, notice I have the difference of two functions, and then the sum, and then the difference. By the linearity rules, I can just take the derivative of each function and then subtract and add as indicated. So I can take the derivative with respect to x of 7x cubed minus the derivative with respect to x of 5x squared plus the derivative with respect to x of 10x minus the derivative with respect to x of 4. So these are the linearity rules. Furthermore, constant multiple rule is also one, right? These are all constant multiples of functions here. I can pull those out by linearity rules. In other words, this becomes 7 times the derivative with respect to x of x cubed. So that was using this linearity rule that, right, the constant can come out, right? Constant can come out. Same thing here, this 5 can come out. And here the 10 can come out. What's the derivative with respect to x of 4? That's 0 by what? The constant rule. That's the constant rule. Right? Derivative of any constant is going to be 0, right? Because the graph of 4, horizontal line. Slope everywhere is 0. But let's take a look at what we have here. What's this? What's the derivative with respect to x of x cubed? That's the power rule, right? This is the power rule. That's the power rule. Bring the 3 down and subtract 1 from the power. Minus 5 times what? This is also the power rule, right? The derivative with respect to x of x squared, bring the 2 down. X to the first power, it's just 2x. And then plus 10, what's the derivative with respect to x of x? That's just what? 1. This is a line of slope 1, right? Or you can use the power rule. You can bring the 1 down. X to the 0 power is 1. I get 1. Of course, this was 0. Clean this up. 7 times 3 is 21x squared. 5 times 2 is 10. 10 times 1 is 10. There is my derivative. Now, some of you have done this before. Some of you haven't. Okay. I took this step by step using the linearity rules and the power rule, the constant multiple rule, step by step. A lot of you will be able to go right from this to this. You'll simply say 7's a constant multiple pulled out, x cubed, bring the 3 down. 3 times 7 is what? 21. Subtract 1 from 3, I get 21x squared. Then what? Bring the 2 down. 2 times 5, 10. Subtract 1 from the power, x. Derivative of 10x, it's just a line of slope 10. Is 10. Derivative of any constant 0. So a lot of you go right from here to here, and that's fine. And that's what I want you to do. Polynomial, finding derivatives of polynomials should be easy. Okay, but here I want you to say, that's easy. Imagine had we done this with the limit definition, right? You would have to evaluate p at x plus h, and you'd have 7, x plus h cubed minus 5, x plus h squared plus 10x. You know, and expand that all out. You're going to have a long stuff. You're going to have a whole page worth of work, or more, several pages probably, right? It's a lot of work. But here now with these rules that we've developed, shortcuts, if you will, very quick to get the derivative and easy, pain-free. Now, close with this. Let's find the equation of the line tangent to this function of x equal -1. Okay? So we've been doing this with the limit definition, but now we don't need it anymore. We know that the slope of this line, m, is equal to what? The derivative of the function at -1, right? We're looking at x equal -1. And this is the derivative right here we just found up here. So I'm going to use that result, because this is the same function, by the way, that we were talking about. And so it's 21 -1 squared minus 10 times -1. Just evaluate that, and if you do, you're going to get 41. I'll have you check that. What's the point of tangency? What point do we pass through on the graph? Well, it's x is -1 comma what? P of -1. So I need to evaluate the original function at -1. So P of -1 is going to be 7 times -1 cubed, 5 times -1 squared, plus 10 times -1, minus 4. So just plugging into this original function, right? And that gives me -26. All right. So the point is -1 comma -26. And so with this information, I can now find the equation of my tangent line. Here's my slope, m. This is my point x1 comma y1. And so if you remember, the point slope equation for a line, y minus y1 is -26 equals m, which is 41. X minus x1 is -1. I get y plus 26. There's my equation. And I'll let you solve for y. You should solve for y, ... I'll let you fill in the steps there, but you should be getting 41x plus 15. There's the equation of the tangent line. So very quickly we can do that now. A problem that we started with, which was find the equation of the tangent line. That was the big problem that we started at the beginning of the semester, right, or the beginning of this course, right? That was the problem motivating us in calculus, and now we can do this for polynomial functions relatively easy now at this point. So this is a big step in our progression, and what we're going to do from now on is we're going to find shortcut rules for the derivatives of other functions, products and quotients of functions. We're going to look at the trig functions. What's the derivatives of the trig functions? The inverse trig functions. We did exponential e to the x, but what about 2 to the x or 3 to the x? We're going to do the log functions, right? Natural log function and others. So, and then some other techniques in there. So we've got a journey ahead of us as we develop these rules, but they will be much easier than trying to continue with the limit definition.